Okay, good morning everyone, Dr. Nat here. So you are in ENG 3004, Engineering Statistics. Make sure you're in the right class. Okay, so I'm going to keep it like this. I'm not going to do slideshow because I need to write on it, okay? So points to ponder, activities pertaining electrical and electronics system are basically surrounded by uncertainty. But before that, let's do a little recap on what we have learned last class. New slide. Okay. So what have we learned so far? Anyone? What did we what was it? Again?
The types of graphs.
The types of graphs. Right? What are the graphs that we mentioned? We have bar chart, right? We have line graph.
Chart.
Stem and leaf.
Histogram.
We have the histogram, yes, for frequency.
Pie chart.
Pie chart,
We have
yes.
a leaf graph.
Again?
Is it called the leaf graph?
The stem and leaf graph, yes. The stem and leaf graph. Usually we use it to compare between two sets of data, but it only works if the data is small, correct? What else? Did we learn anything else apart from that?
Sample variance and population variance.
Yes, the most important one. Sample variance and population variance. When do we use sample? When do we use population variance?
Sample is when we're taking a chunk of a population.
Mm-hmm.
And the population is when we're taking it as a whole.
Yes. So what does the sample variance tell us? Why do we use it? Why do we need
it represents the population?
Yes, it gives us an approximation of the entire population, even though we're only taking like a small chunk of that whole data, because typically we deal with thousands and thousands of data and we don't want to, calculate all of this data. So we just take a part of it and we get roughly a good approximation. How does the approximation work? How do we make it work? Why is it true? What was the correction applied? We applied something different than the formula of population variance. What was it? How is the sample variance different than the population? Again? The Bessel correction, yes, the Bessel correction. So it is important for you to distinguish between those two formulas. Sample gives us approximation, but how does that approximation work? It is because we applied the Bessel correction to eliminate any bias, okay? So good, I think everyone got it so far. So I'm going to continue with our new topic for today, which is uncertainty, or we're going to start with probability. So points to ponder, activities pertaining electrical and electronic system, which we deal with a lot today, are basically surrounded by uncertainty. For example, you have like a battery. The battery says that it has 5 volt, but it is not exactly 5 volt. It has some uncertainty to it. Sometimes it's 4.9993, sometimes it's 5.0001. So that is the uncertainty, but they give you an approximation. Okay, so on average, this battery is 5 volts. So typically that is how the values are labeled. But in reality, we have those uncertainties going on. Okay, for example, the chances that people will be hit by lightning during rainy season, the chances of that power system to fail, the accuracy of an error detection mechanism. We can never be certain of these events. Okay, quite boring. Next, so probability. Probability allows us to use sample data to conclude about the population. We talked about this previously. Probability distribution models some random variables on the population. We're going to discover this in a bit. Probability can be calculated given data obtained from observations. Also, we're going to talk about that. An experiment is an activity or process by which an observation or measurement is obtained. Okay, so when you're doing something, let's say you are recording the weight of breads. Let's say you own a bakery, you want to sell breads, the same type of breads. So you want to, record the weight of the breads so that all the breads that you are selling have approximately around the same mass or the same, what do you call it? The same, what do you call it? Weight, the same weight. You want to sell breads that are of the same weight. Okay, so that is called an experiment. The act of doing something, the act of recording data is experiment. For example, over here, we have, wow, this is so huge. Okay. We have this experiment going on here. Is given, we have an example here of an experiment, record an age. So I'm going to record all of the students in my class, but they have like around 19 or 19 years of age or 18. So it's roughly the same. But if I'm talking about a huge population, like the students in the university, so you would get like more data, and the data would be like between 18 to 22, let's say. So the act of getting the data is called experiment. And from this experiment, we get events. For example, we get this event, we get person is 30 years old. And then the second event, a person is older than 65. And another experiment example is tossing a dice. You have two events going on because you tossed it twice. So the first event is you observe an odd number, and the second event is you observe a number greater than 2. So the act of recording is called experiment. Sorry, the act of getting the data is called experiment. And what comes out of the experiment is called events. So these are two terms that you need to remember. Okay, so we talked about experiment and also event. So probability can be calculated given the data obtained from the observations. Probability can be calculated given data from the observation. These are the observation or the events. Okay, moving on. Overview of probability. So another example of an experiment and events is meeting aliens, alien encounter. I don't know why they use this example. Let's just go with it. So the events is A, an alien encounter in Malaysia. What is the probability of an alien encounter in Malaysia? P in bracket A, I think this is called bracket, P in bracket A is equal to 0 because the probability of that happening is impossible. So it's 0. So what about Toyol encounter? For those who are not from Malaysia, Toyol is actually like, I don't know how to describe it. I think it's a mystic being that steals money. And it's very, very small from the stories that I've heard. I have never seen one. Okay, so what is the Toyol encounter? This is the experiment. We are recording the data. How many times have someone seen Toyol or encounter a Toyol? So B, the event is B, a Toyol encounter in Malaysia. What is the probability of event B? And someone said, I've seen a Toyol before. So the probability is no longer 0. So you have some value over here. Let's not trust this data. It's not, it's just an example, okay?
Yeah, no.
Yes? Soalan ke? Do you have any questions? No questions? Okay. Okay, so we talked about experiment, we talked about events, and those are where we get the data. What about sample space? This is another term, our third term for today. An event that cannot be decomposed is called a simple event. An event that cannot be decomposed is called a simple event. We saw events just now. For example, a person is 30 years old. Can I further decompose it? I don't think so. That's the data that we have. Can I break it? Can I break this data into multiple datas? No. So we call this simple event. Okay, an event that cannot be decomposed is called a simple event. It is denoted by E with a subscript. For example, you have 5 data or you have 5 events. So you're gonna write it like this: E1, E2, E3, capital E with a subscript. This is how you write it. Each simple event will be assigned a probability measuring how often it occurs. For example, we talked about the events that happened here. So we are trying to find out what is the probability of someone who is 30 years old in UPM. We're trying to find out what is the probability of someone that is 30 years old in UPM. So I'm going to say P of A is equal to whatever value that I get. I'm 30 years old. So that is, I'm already contributing to the data. Okay, but we have to like measure more than 1% lah, of course. Okay, so each simple event will be assigned probability, measuring how often it occurs. The set of, I think I did not give you a good example. We're going to discuss this more later. The set of all simple events of an experiment is called the sample space. Now here, they labeled all the events within a bracket. So E1, event 1, event 2, event 3, event 4, event 5, and 6. And all of these elements are enclosed by a bracket, and it is equal to S. S is your sample space. I know this is pretty boring because we just started probability. We have to know how to write probability. You have to know the terms first. Quite boring. Okay, so S is equal to, in bracket, you enclose your events or elements inside the bracket. So E subscript something is your events. Okay. So for example, you observe an odd number. This was observed in event 1 and event 3 and event 5. You observe a number greater than 2. You saw this in event 3, event 4, event 5, event 6. But this entire data is S is equal to E1 in bracket up to E6. This thing lah, this thing over here. Okay, but you can categorize the events. Okay. Okay, so S is sample space. You have the bracket, and inside is events. The simplest experiment to which probability applies is one experiment with two possible outcomes. For example, we are making poppets at the factory. You are an operator that makes poppets, where the outcomes are defective or non-defective. When you're making something, you're fabricating a product or a toy. The one thing that you want to know is it good enough to be on the shelf? Is it defective or non-defective? So those are the two outcomes when you are making poppets. So this can be abbreviated as sample space S is equal to, in bracket, non-defective and defective. You only have two outcomes ataupun or two events. So the braces are used to enclose the elements of a set. So apart from calling these events, apart from calling these things inside the bracket as events, you can also call them as elements. Elements is within the bracket, within the braces. Okay. If you have any questions, you can interrupt me. Okay. Okay, so still on the same topic, sample space. Another example, if we examine 3 poppets in a sequence, you are the operator in the factory. Instead of examining 1 poppet at a time, you examine 3 at a time. Meaning to say, like, you have 3, it moves, you have 3, it moves, you have 3, it moves. So you have to work quicker. So you are examining 3 poppets at a time. So what is the outcome for the experiment? It is any sequence of n's and d's of length 3. So how do you write this? Sample space, n, comma, nnd, comma, ndn. What does this mean? This is non-defective, non-defective, non-defective. Great. This batch can be packaged into one box. This is non-defective, non-defective, defective. Not good. So you have to resend it over to the whatever thing, I don't know. And then non-defective, defective, non-defective, not good, not good, not good. So this is especially important if you really have to produce things in bulk. Like, for example, you have to package 3 poppets in one box for the shop. So you observe this in sequence. So you can, so the point here for this slide is that not only your events can be in single form, which we have seen earlier, it can also be in other lengths. Can be 3, can be 5, can be any size actually. So just keep that in mind. Okay, so we talked about sample space, we talked about events, we talked about experiment, which is the act of recording data. And we know that within the braces of a sample space, we call those E subscript as events or elements. So now what is mutual exclusive? Two events are mutually exclusive if they do not share any common elements. For example, observing student in a classroom. So this is M, observing a male student. This happens in event number 1, 3, 5, 7, and F, observe a female student, E2, E4, E6. There's no overlap between M and F. Okay, because there's no overlap. You either identify as a female or a male. And M, of course, this is up for debate considering the times that we are in. M and F are mutually exclusive of each other. Okay, so please don't take to heart if you don't identify with this. It's just math. Okay, so probability of an event. The probability of an event A measures how often we think A will occur. I told you about this earlier. So we write this as P in bracket A. Suppose that an experiment is performed n times. The relative frequency for an event A is the number of times A occurs over the total the total data that you record. N is the total data that you record. Okay, bear with me. I know this is very lengthy and not very interesting, but we have to learn this. So the probability of A is the number of times A occurs over the total data that you record. So let's say you record data 10 times, right? You record data 10 times, you record 10 students in the class. What is the number of times that you encounter a female while you are recording this data? Let's say you have 6 females in the class and 4 males in the class. So what is the probability of encountering a female? So it is 6 over 10. The probability of encountering a female is 6 over 10. 10 is the number of total data that you record, and 6 is the number of times that you encounter a female when you're recording data. Okay, so you can also write it as this, frequency F over N. Okay, so probability must be between 0 and 1. Why? Does anyone know why? Why does it have to be between 0 and 1? Why can't probability be 2? Anyone wants to guess? It's okay if you're wrong. It relates back to this equation. Why is probability between 0 to 1? Why can't it be greater than 1? Anyone?
Because it is a percentage.
Because it is like a percentage, correct. So if you record data 10 times, you encounter, for all the data, you encounter 10 females. So 10 out of 10, the frequency that you encounter a female over the total number of data that you record is just going to be 1. You can't have 12 females when the number of data that you record is only 10. So it doesn't make sense. So probability is like percentage. You can only go from 0 to 100 or 0 to 1. Okay, that is correct. So if an event A can never occur, which means that in the 10 data that I record, I don't ever see a female. So the probability of encountering a female is 0. Whereas if all the 10 students that I record is all females, then the probability of encountering a female is 1, which is 100%. So the sum of the probabilities for all simple events in S equals 1. So for example, we talked about male and female. So I said we have 6 female and 4 male. So this would be 6 out of 10. And if I write this in decimal, this would be 0.6. And 4 male is 4 over 10. If I write this in decimal, it is 0.4. And the sum of these two guys, I mean these two data, has to be equal to 1. Cannot be more than 1, cannot be less than 1. So it has to be equal to 1. Okay? So the probability of an event A is found by adding the probabilities of all simple events in A, which we discussed earlier. For example, we are tossing a dice. So events, observe an odd number. The probability of this happening is 3 over 6, for example. So you can, of course, you can simplify this to become 1 over 2. 3 divided by 6 is 1 over 2. And the event of you observing a number greater than 2 when you toss a dice is 4 over 6. You toss a dice, the number is greater than 2. The probability of that happening is 4 over 6. Why? Because a dice 1, 2, 3, 4, 5, 6. The probability of greater than 2 is just these numbers. So 4 over 6. So you can simplify this number to become 2 over 3. And then the probability of observing a 6 is just 1 out of the 6 times that you toss it. So 1 over 6. So when you add these together, it should be equal to 1. 3 plus 4 is 7. 7 plus what? Sorry. This is not equal to, did I get this wrong? Yep. 1 over 2 plus 2 over 3 doesn't sound very convincing. Can someone calculate this for me? 1 over 2 plus 1 over 3 plus 1 over 6, is it equal to 1? I think it should be. No one has a calculator? You're learning maths and you don't have a calculator? That's odd. 1 over 3.
Doctor, I think it's 8 over 6. 1 over 2 plus 2 over 3 plus 1 over 6.
8 over
It's
6,
8 over
yeah.
6.
This is not equal to 1. Okay.
Yes.
The probability of an event A is found by adding the probabilities of all simple events in events A. Okay, it shouldn't be equal to 1 because it's not measuring the same thing. Okay, they are talking about event A, which makes sense, but okay. I need to get back on this one. Okay, so event A is observing an odd number. Okay, odd number is this guy, and this guy. So it is 3 over 6. Observe a number greater than 2. So we're not talking about odd versus, what's the opposite of odd? I don't know. Even number. Yes, even number. We're not talking about odd versus even. When we're talking about odd versus even, then the probability should be equal to 1. So let's see. So A is observe an odd number and D is observe even number. Whoops, sorry for the bad handwriting. So even number, let's circle it. 1, 2, 3. So when we're talking about even number versus odd number, then the probability should be equal to 1. So P of D is 3 over 6, which is also 1 over 2. So these two together will give you 1. But when we're talking about, when we're comparing like different aspects of the data, then you can't add it like that. That was my mistake. Okay, I hope that is clear for everyone. Is that okay with everyone? Or are you guys?
Yes.
Yeah, all right. Okay, so exercise number 1, toss a fair coin twice. You have a coin. This is an ugly coin. This is the heads is the top and the tail is the bottom. So H is heads, the top, and tail is the bottom. What is the probability of observing at least one head? So you toss this coin twice, right? You toss it twice. So the first time that you toss it, you can get a head or a tail. That's like common sense. The first toss, you can get either a head or a tail. Versus when you toss it another time, you can also get another head or a tail. So the first toss, and this is the second toss, you either get heads and heads, or you get heads and tails. Or if you toss the first time, you get tails. The second time you toss it, you either get a heads or a tail. So this is HH, HT, TH, TT. So these are events. This is the outcome of your experiment. So what is the probability of this event occurring? So the total number of data that you have or events that you have is 4. So the probability of this happening is 1/4. This is the frequency that is going to happen over n, f over n. What is the probability of HT happening? You only see it once, so 1/4. What is the probability of TH, tails and heads happening? You see it 1/4. And then tails and tails also 1/4. So the probability of these guys in total will give you 1. But each is 1/4. P of HH is 1/4. P of HT is 1/4. P of TH is 1/4. Now someone will argue, but Dr. HT and TH looks like the same thing. Why can't we make them like the same event? We're talking about the first toss and the second toss. So here the order actually plays a role, unless that I don't care the order that it goes. Then yes, you can add them together. But here we're specifically talking about the first toss versus the second toss, and they put it in this order. You have the first toss and the second toss, and they combine that together. So here the order is important. Therefore, you can't group these two things together. Okay. So, but of course, there are cases where you don't really care about the order and you can group them together. So HT plus TH will become 2/4. Okay. So what is the probability of getting at least one head? Now we're not talking about the probability of each event. We're talking about getting at least one head, at least. It doesn't matter if it happens in the first toss, it doesn't matter if it happens in the second toss. I just want at least one head. So here, this is at least one head. This is at least one head. This is at least one head. So I have 1/4 plus 1/4 plus 1/4. That gives me 3/4. And the probability of getting at least one head is 3/4. Any questions about this example or exercise? Is everyone okay with this?
Okay,
No.
Any questions? No questions. Okay, so everyone got it. Okay. All right, so exercise number 2, a bowl contains 3 M&Ms, just 3, 1 red, 1 blue, and 1 green. So let's draw it because why not? Why is this not working? What? Draw. This is blue. 1 red, 1 blue, and 1 green. So M&Ms are supposed to be circle, but this is an Eclipse M&Ms. It's my brand. Okay, so you have these 3 in a bowl. My bowl is red. Don't really care about the bowl. A child selects 2 M&Ms at random. So this is the hand of a child. He's trying to take only 2 instead of 3 because his hands are small. My M&Ms are big. What is the probability that at least 1 is red? So now we don't care about the order because there is no first grab versus second grab. This child is taking 2 at a time. There's no order here. Okay, so the first M&M, oh, but it selects 2 M&Ms at random, not together, or is it one at a time? Based on this, okay, I don't think it matters. Okay, so let's say the first M&M that he got from the 2 is red, and the second one should be either blue or green. It can't be red and red, right? So if the first one is red, the second one should not be red because there's only one red. You can't have another red. So it's either red with blue or red with green. But if the child takes 2 and the first one that he got is blue, the second one should either be red or it should either be green. And if the child takes a green M&M, the first M&M is green, the second one should be blue or either red. So here we combine these two. We get red, blue, red, green, blue, red, blue, green, green, blue, green, red. Okay, so the probability of these events happening is 1/6. The frequency of red with blue is 1/6, red with green 1/6, blue with red 1/6, blue with green 1/6, and you get the idea. Why is it 6? Why is it 6?
Six possibilities.
Is 6.
Again, sorry. What was it? Why is it 6?
Because there are 6 events.
Because there are 6 events in total, correct. So the probability of getting red first and second one blue is 1/6, 1/6, and so on. So this is the frequency, and 6 is n, the total number of events. So now it's asking you, what is the probability of getting at least one red? One red. So this one is yes, 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 and yes. So you have 1/6 plus 1/6 plus 1/6 plus 1/6. You have 4 times. So it becomes 4/6 or 2/3. Okay, because of the question, at least one red, the order doesn't really matter. So I'm not sure if we should rephrase this question to select 2 at a time or 1 at a time. But I don't think it matters because that's not the question. Okay, but it confused me a little bit. Okay, moving on. So we talked about mutual exclusive. It means that the data or the events do not overlap with each other. What was the example that we talked about just now? It was female versus male. It is mutually exclusive. And another example would be this guy. There's no red, and this one has red. So it is mutually exclusive in the sense that one has red, the other has no red at all. That can be mutually exclusive as well. But they have overlaps in other sense, such as green and blue. So if we're talking about red, we can say that it is mutually exclusive. This group, versus this guy, this group. You can say that it is mutually exclusive in terms of red. But in reality, they have overlaps. Okay. What else? Mutually exclusive, male and female. I think that's like the easiest one that we can remember. And then we talked about F/n, the frequency of an event happening over the total number of events. Okay, moving on. So counting rules. Sometimes we cannot list out the outcomes easily as the n is quite large. So it was fairly simple when we had like 3 M&Ms and we just wanted to select 2. So you only had like 6 data or 6 events happening, right? But what if you have like 100 M&Ms and 100 M&Ms of different colors? Not sure if that's possible. And you just want to select 2. So there's like a lot of combinations going on. Your n will be crazy. Your n will be super large. So we use the counting rules when that happens, when we can't list out the events one by one because the n is too big. Fortunately, there are several counting rules that can be applied, and these are the 3 counting rules that we are going to learn. The first one is the product rule. Second one is permutations. The third one is combination. So remember, counting rules are not probability. When we apply these things, we are not calculating probability. We are calculating the n. Okay, but counting rules can be used to deduce the probability. It will help us to deduce the probability later on. Okay, so the first one, what time is it? 9:41. Let's take a 10-minute break. Come back at 9:50 and then we'll continue. If you have any questions, you can ask me now during the break. Or if not, please go to the bathroom, get your drink, get your snacks, whatever. I'll see you back at 9:50.
Okay, Doctor.
Okay. So any questions?
No.
All right.
Hello.
Yes?
Doktor. Nak tanya pasal mutually exclusive tu. Saya tak faham lagi.
Oh, mutual exclusive. Okay. So, okay. The M&M's example for mutually exclusive is not that accurate. So let's go back to the example that we talked about, male and female data. So remember I told you I was recording 10 students and I wanted to know within these 10 students that I'm recording, who is a female, who is a male. And from here, we found out that we have 6 female versus 4 male, right? So these are simple events whereby we have 6 female, this is 6 simple events, and we have 4 male, 4 simple events. So if I were to portray this as a Venn diagram, are you familiar with Venn diagram? Tahu tak Venn diagram tu apa? Tak ingat? You don't remember? Okay. So if I group this data, right? I have 10 students. This is all the students. I'm putting all the students here. Okay. 4. Okay. So I am enclosing all the male together as one group. Okay. Within this group, this is male group. I have 4 inside this for data. And within the female, I enclose this as female. And within this is all female data. And as you can see over here, they don't overlap. They don't share any common traits. And that is usually the case with simple events. Your data is either defective or non-defective. Your data is either female or male. They cannot be overlapped. Why is defective versus non-defective? You can't overlap, it's mutually exclusive because you cannot have an item, you cannot have a poppet that is both defective and non-defective at the same time, right? If it's defective, it is defective. If it's non-defective, then you can sell it. It can't be both. Correct?
Okay, faham. Maksudnya dia tak ada macam tengah-tengah tu lah kalau ikut Venn diagram tu.
Betul. You can't have both at the same time. It has to be one or the other. So that is mutually exclusive. That's a good question because I think I didn't explain that well enough. The one that we talked about for M&Ms, scratch that example. I think it's going to be confusing. So for this guy, I said, if you're talking about red, then yes, it is mutually exclusive. Like just forget about that example for now. So how do I draw the Venn diagram for this data? So if I say RB, RG, BR, what is the overlap between these three data is that they are all red, right? They have at least one red. So they overlap together in a sense that they share a common trait where they have at least one red. So this is not mutually exclusive because they share a trait. And here you can't really call this simple event because you can actually break it down. You can break it down to red and also blue. But when you're talking about simple events like non-defective versus defective, where was my example just now? Where's back here? Here you don't have that overlap. It's either female or a male or defective versus non-defective. Then this is mutually exclusive. Okay, there's no overlap. It has to be one or the other, cannot share the same trait. Okay, any other questions? No questions? Okay, if you have any, you can ask. Excuse me. You can also type it in the chat box if you have any questions. Okay, I hope everyone is back from their break. So let's continue with the product rule. Okay, so the product rule again, this is one of the counting rules. What does the counting rule do, or What does it tell us? The counting rule tells us what the number of n is. If we cannot list out all the n's, remember your n so far that we have seen is like very small, either 6, 4, you know, it's very, or you can list it down by hand. But what if your n is very, very big, like 100 or 1000? So probability deals with data, a lot of data. So most of the time the n will not be 6 or 4. So we need to know these rules so that we can approximate for the n's, not approximate, we can find out the n's. Okay. For example, we're still using the toss 2 coins example. We have seen this example earlier on. Where's my pen? It's gone. Uh-oh, my pen is gone. Give me a minute. This is the technical issue, which is my pen. Oh my God, it's not detecting. Pause recording. Tune recording. Okay, sorry about that. Let's continue. Okay, so again, we are discussing the counting rules. We're going to start with the first one, which is product rule. So what does the product rule tell us? It tells us the number of n. So how do we find out the number of n? So here, if an experiment is performed in 2 stages with n1 ways to accomplish the first stage, for example, you're tossing a coin, how many ways or how many events can you get from tossing the coin? You can get 2, right? You either get a heads or a tail. So you know that you only have like 2. This is 2 for tossing a coin. And you toss the coin again. What is your outcome? What is the events that you get from tossing the second coin? You either get a heads or a tail again. So this is also equal to 2. So if you have 2 ways to accomplish the first stage and 2 ways to accomplish the second stage, then the total number of n, or the total number of data that you can record, or the total number of events that you can get, is n is equal to n1 times n2, or the product of n1 and 2 ways to accomplish the experiment. This rule can be applied for if you have like many stages. For example, you have 10 stages. Each stage you have 2 ways to get, for example, you are tossing coin 10 times, then that would be n1, n2, n3, n4, n5. Why did you choose 10? Let's just choose 6 and 6. So each of this, you know that you can either get a heads or a tail. So each is 2. So how do you calculate the total number of n? 2 times 2 times 2 times 2, 6 times. Okay, so that is your capital N, or the total number of events. So let's compare with the one that we listed out manually. Okay, example, toss 2 coins. The total number of simple events is 2 times 2 equals to 4. Let's compare. Okay, this was the example that we talked about earlier. Toss a fair coin twice. What is the probability of observing? No, we just want to know what is the number of events. We want to know the number of events. So here, the first coin, you can either get a heads or a tail. The second coin, you either get a heads or a tail. And we talked about using the product rule that was 2 times 2 equals to 4. And indeed, when you do it manually, you list it out manually like this, you do get a 4. So the product rule is legit. Okay. So what if you have a third coin? Then again, you have 2 times 2 times 2. You have 6 events. Okay. Sorry, 8 events. Okay. So any questions about the product rule? Is everyone okay with it? Any questions? So it's quite easy, right? Okay, moving on to the to the example. A homeowner doing some remodeling requires the service of both plumbing contractor and electrical contractor. Okay, so one is plumbing, one is electrical. If there are 12 plumbing contractors and 9 electrical contractors available in the area, you just want one of each, right? But in that area, in your home, in your, what do you call it? In your, I don't remember my English. In your region where you stay, you only have 12 plumbing contractors and 9 electrical contractors. Okay, you need to select one plumbing contractor and 1 electrical contractor. How many ways can the contractors be chosen? How many ways? So if we denote the plumbers by P1, blah, 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 up to P12, this is P, plumber, and the electricians by Q1 up to Q9, because you have like 9 electrical contractors, this forms pairs of PI, Q, J. For example, if you select the, let's say, if you select P1, and for the second one, you select Q1, so you have 1 pair. And the second one, P2, Q1, this is your second pair. And then P3, Q1, you have your third pair. And we haven't even started with Q2, Q3, Q9, etc. We haven't even started. So there are a lot of data or pairs or events that we need to account for. So how do we do this? We use the product rule. So if there are 12 ways to select the plumber and 9 ways to select the electrical contractor, so that would be 12 times 9 over here, and n is equal to 108 possible ways of choosing the 2 types of contractors. Again, there are 12 ways to select plumbers. There are 9 ways to select electrical contractors. I don't have time to list out all of it. What do? I use the product rule. So now I know the total number of possible ways to choose the contractors, or we can call this as events. Okay, is that okay with everyone? Any questions about this one? Okay.
So far, okay, Doctor.
Oh, okay. Okay, moving on. Next exercise, toss 3 coins. So now we're tossing 3 coins. We know 1 coin has 2 outcomes, either a heads or a tail. So if you're tossing 3 times, this is your first stage, second stage, third stage. And each stage, you know that there are 2 possible ways of getting a heads or a tail. Sorry, there are 2 ways of outcome. Sorry, 2 outcome of tossing a coin. So this is hard. Transitioning from the plumbers to the coin. And the second stage, you get 2 ways or 2 outcomes. And for the third stage, you also get 2 outcomes. So the number of n is 8. So they are repeating this example, toss 2 dice. Toss 2 dice. And you know that dice, you can have 6 possible outcomes or 6 possible results or 6 possible ways, right? So 1 dice, the first stage, you get 6. 1, 2, 3, 4, 5, 6. You either get between those numbers. And for the second stage, again, the same thing, 6. So 6 times 6, your n is equal to 36. So this is not too bad versus this one, it's 108. I don't have time to list it out. Okay, next exercise. There's a lot of exercise and examples because I want you guys to understand. So forgive me if we are like dragging this, okay? So example, in data networking, so this is like communication stuff. A packet can take 2 routes. A packet can take 2 routes from router A to router B. From router A to router B, so let's label this. From A to B, you have 2 possible ways. And from router B to, 3 routes from router B to router C. So 3 routes from router B to router C. And 3 routes from router C to D. So my face is over here. Okay, so you have 3 routes from C to D. how many possible ways, how many possible A to D routes are available. So let's say you select this route, and then you select this route, and you select this route. This is only one route, one possible way. And then you select this one, and this one, and this one. This is another possible way. You select this one, you select this one, you select this one. This is another possible way. You get the idea, there's a lot. So this is two possible ways of selecting the route. And for the second stage, you have three possible ways of selecting the route. And for the third stage, you have three possible ways. So what is the total number of events or pairs that you can get? Not pair. What is the total number of events that you can get? 2 times 3 times 3. 9 times 2 is 18. So there are 18 possible routes that I can get from this architecture. Okay, so if one link between router B and C, okay, dia cakap, one link between router B and C is down. That leaves us with, this guy is down, no longer usable. This leaves us with only two possible ways. So now it becomes 2 times 2 times 3. First stage is 2, second stage is 2, third stage is 3. So that is 4 times 3, 12. So the number of possible ways has reduced by 6, even though we only eliminated one route. Okay. Oh, this is the same one. Okay. So we talked about the product rule, whereby we identified the stages, and for each stage, how many possible ways or how many outcomes that you can get. We talked about tossing a coin versus selecting plumbers and electrical contractors, and you get the idea, dices. So now we have a different kind of scenario. So consider a basketball team of 15 players on its roster. Okay, this is typical, even though I don't know basketball much. How many ways are there to select 5 players for a coming game? So you know that you can only select like 5 in the court, right? And the rest are going to sit on the bench. So from the 15 players that you have, you want to select 5 only. Here, there are 15 players or n distinct individuals. How many ways are there to select a subset of size R? So this is rephrasing the question in mathematical description. You have 15 players. This is your total n number of distinct individuals. And let's represent the data like this. Is this 15? I don't know. Let me rewrite this, redraw this. Let me draw it like this, okay? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the numbers represent each individual. Ali ke, Rosmah ke, siapa lagi? Hisham ke, Nadiah ke. Okay, all of this is within the 15. Doesn't really matter. Now I just want to select 5. This is my whole data. My whole data is n. From this n, I want to select only 5, and this 5 out of the n, out of the total number, is called a subset. So 1, 2, 3, 4, 5. So I select this guy. This is 5 out of the 15, and I call this a subset. It is within the whole data subset. Okay, so another example of subset is the sample versus population. You're taking sample, is a chunk of the whole data, right? That is a subset. You are selecting only 5 out of the 15. That is a subset. What else? Out of the 60 students, only 30 is in my AutoCAD class. My AutoCAD class is a subset of the total 60 students. Those are subsets, okay? So here we only talked about the question. We haven't like approached it or anything else, nothing yet. So what do we do over here? How do we select 5 out of the 15? So moving on. Those are the questions that I want you guys to think about first. Scenario number 2. Oh, sorry. Before I move on. For each individual, I have to determine who is the point guard, who is the shooting guard, who is the center, who is the small forward, who is the power forward. So not only is it already hard selecting 5 out of the 15, it is also very hard to know what are the possible number of ways of selecting point guards, shooting guard, and etc. So you have that going on for this scenario. Quite hard, right? How do we find out the number of possible ways to select 5 out of the 15, whereby each individual has to be assigned a role in the team? Okay, moving on. Scenario number 2. Consider a computer shop that sells 10 different laptops. This is like a poor shop, only has 10. Oops, sorry. How many ways are there to select 3 laptops if the shop has only 3 displays? Now they have 10 laptops, and I told you before it's a poor shop. They only have 3 displays, and the display is just a table. Quite sad. So out of the 10, this is our data: 4, 5, 6, 7, 8, 9, 10. So I am only allowed to select 3 out of this 10. What are the number of possible ways to select these 3 out of the 10 laptops? Now, I don't have, the question did not mention about selecting a specific order or a specific display. I don't have like display number 1, display number 2, display number 3. I don't have that. I just said, I just want to select 3 and I want to put it on the table. That's it. I want to have a subset of size 3 and I'm choosing it from 10. So the 10 laptops are n distinct objects. How many ways are there to select a subset of size R? So again, this is our R, and the total data is n. The total distinct individuals or distinct objects are n. Okay, so what can you tell me the difference between scenario 1 and scenario 2? Anyone wants to try? What's the difference?
The scenario 2 has the specific.
Scenario, again, scenario apa? No, you don't want to try it anymore?
Has a specific.
So you're saying scenario 2 is not specific.
Specific.
Oh, scenario 2 is specific. Scenario 1 is?
I think not specific.
Not specific. Why? Why is
They
that?
have distinctive position.
Scenario 1 has the position. Scenario 2 does not have any specific position. Okay. Other answers? Only 2 guesses out of the 60 students that I have here. I only have like a subset of 2 out of the 60N. Come on, guys. Increase the subset. Other guesses? What's the difference between
Specific
scenario 1?
order and
Mhm.
scenario 1, you need a specific order, and scenario 2, it doesn't matter.
Scenario 2 doesn't matter. Correct. For scenario 2, I just care about selecting 3. I don't care which display it goes on to because there's only like a table. I'm just putting all 3 together. There's no order. Versus scenario 1, if I'm selecting 5 out of the 15 players that I have, from the 5, I have to like care who becomes number 1, who becomes number 2, who becomes number 3, etc. Right? So the difference between scenario 1 is that it has order, the order meaning the position or the roles, versus scenario 2, you just care about selecting the subset. You don't care the order of selecting the subset. Okay, so approaching these 2 scenarios is different. So the first one, permutations, ordered subset. So the basketball example that we saw earlier is an ordered subset. I want to select a subset of 5, but I also care the roles that my subset gets. So the number of ways you can arrange n distinct objects, taking them r at a time, we denote it as this: permutation, n distinct individuals, choose r. Again, permutation, p is almost like the same as probability, but this one is like italics a bit. Permutation, I have n distinct individuals, I choose r. Choose r is the subset. So this is the equation that you get, n factorial notation. I think that's the right word for it. Factorial. This is factorial. Okay, n factorial, and then n minus r factorial. So this n is from the n distinct individuals. The r is your size of your subset. And then you expand your equation, where n factorial is n times n minus 1, n minus 2, etc., etc. And if somehow you have value of 0 factorial, this is just equal to 1. So don't panic when you see 0 factorial, it's just equal to 1. 1 factorial is also equal to 1. Okay, so just putting it out there, whenever you see this, you see a 0 factorial, it's just equal to 1. Okay, so here the order of choice is important. So very, very important to understand the scenario. Is it ordered or not ordered when you're choosing the subset? Okay, so this is another example: permutation 4, choose 3. 4, choose 3. So 4 minus 3 factorial down here. So 4 minus 3 is 1. 1 factorial is just 1. 4 factorial, you expand this, it becomes 4. 4 minus 1. 4 minus 2. 4 minus 3. So this becomes 3. This becomes 2. This becomes 1. 4 times 3 times 2 times 1. 1, you just get rid of it. 4 times 3 is 12. 12 times 2 is 2, 24. Okay, so let's do an example. Back to the scenario. So we have 15 players as our n. We have a subset of size r. Here, the order is important. So we have to use permutation of n, choose r. So here, I'm going to write it like this. Permutation 15, choose 5. So how do I write my equation? Let me make this bigger. And I need to write this nicer. Okay. Let me use blue. Okay, P 15, choose 5. Okay, so how do I write this in my equation? What was it? N factorial. Okay, n factorial over 15 minus 5 factorial. So now I expand it. This is a lot. I'm quite lazy. Okay, so 15 times 15 minus 1, 15 minus, wait, let me simplify this first. (15 factorial over 15 minus 5 is 10 factorial. So I want to get rid of 10 factorial. So let's try to make our lives easier. 15 minus 1, this is 14. And then 15 minus 2, this is 13. And then 15 minus 3, this is 12. And then we have 15 minus 4, this is 11. And then we don't have space. Make this smaller. Okay, bear with me. I'm going somewhere with this. Okay, so when I reach 15 minus 5, right? I still have like a bunch of other numbers that I have to like expand, right? 15 minus 5, 15 minus 6, blah, 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 up to 15 minus 14, which is actually just 10 factorial. This part over here is just 10 factorial. If I expand it, it's just 10 factorial. So dividing it by 10 factorial, I can just get rid of it, and my life is now easy. So now it becomes P15 choose 5, P15 choose, sorry, permutation 15 choose 5 is just 15 times 14, whoops, times 13 times 12 times 11. As you can see over here, there's no longer the 10. 10 is gone. There's no denominator anymore. It's gone. Okay, so this is my permutation. This is the number of possible ways. What does permutation tell me? The number of possible ways to select 5 out of 15 players in a way that each of the subset, sorry, each of the player gets a role, gets a position. Possible ways. Okay, so any questions about this example? Everyone okay, right? If you have any questions, you can interrupt me. Okay, moving on to the next one. Let me make this smaller. Okay, suppose, for example, that a faculty of engineering, not specific to UPM, has 7 departments, which we denote as A, Department A, Department B, Department C, Department D, Department E, F, G. Okay, so each department has 1 representative on the college student council. What do you call this in UPM? MP, is that right? MP? From these 7 representatives, 1 is to be chosen as chair, another is to be chosen as vice chair, and another will be the secretary. So is this an ordered subset or a non-ordered subset?
Ordered.
So, yes, there's already the answer over here. I just wanted feedback. So here we care about the order because when we are selecting the 3 out of the 7, we care about assigning roles to them. So that is an ordered subset. Okay, so for ordered subset, we have to use permutation. How many permutations of size 3 can be formed from the 7 representatives? So permutation 7 choose 3. So 7 choose 3. Again, we're not going to see the 4 anymore. Get rid of it, cancel it out. So it becomes 7 times 6 times 5. Or if you don't want to expand it like this, you can just expand it up to the 4 factorial over 4 factorial. So just cancel that out. And 7 times 5 is 35. 35 times 6, I don't know. Just use your calculator for that. Okay, next exercise. So a log consists of 5 parts. So you have like 5 parts, sorry. You have like 5 parts. I'm just drawing this in random. Your log doesn't necessarily have to look like this. There's 5 parts. And it should be assembled with the 5 parts. So a quality control engineer wants to test each order for efficiency of assembly. For example, the 5 parts are called A, B, C, D, E. So the quality engineer wants to test A, B, C, D, E, or B, C, D, E, A, C, D, A, B, C. So he wants to test all possible ways of the 5 parts together so that he knows that the log is functioning well. So here it is n is equal to 5. You have 5 parts. And the number of subset is also equal to 5. From the 5, you are choosing 5. What are the possible ways of choosing 5? So here, permutation 5 of 5 gives you 5 factorial, and 5 minus 5 factorial is just 0 factorial. Remember, I told you 0 factorial is just 1. So here, this is just 1. So you expand the 5 factorial to become 5. 5 minus 1, 5 minus 2, 5 minus 3, 5 minus 4. So the answer is 120 possible ways of assembling the 5 parts to make a log. Okay. Did everyone get this example? for exercise?
Yes,
Yeah,
doctor.
Okay, all right. So if you have any questions, you can interrupt me. I cannot emphasize that enough. When you ask questions, you're actually helping your friends as well. Okay, so we move on to or unordered subset. Unordered subset, like the scenario that we have seen with the laptops. You have 10 laptops, you want to choose 3, you don't really care where it goes as long as you get the 3. So how many possible ways of selecting 3 out of the 10? Okay, so here the equation is quite different. The notation is also different. Instead of using P is for permutation, you use C for combination. It is still N choose R. R is a subset, N is the number of objects or individuals. Okay, so here the equation is different in the sense that you have an extra term here, R factorial. Okay, so very important. The notation is different and you have this difference. You have that R factorial in the denominator. Okay, so if we want to apply it to the laptops, right? So C, 10 choose 3, right? 10 choose 3. So this becomes 10 factorial over choose 3 factorial, 10 minus 3 factorial. So expand that how you want and you solve that, you get the number of possible ways of selecting 3 out of 10 laptops. Example, 3 members of a 5-person committee must be chosen to form a subcommittee. Now the norm is when you are selecting subcommittee, you don't really care what position they hold, you just want a subcommittee, right? This is different compared to selecting a chair, vice chair, secretary, etc. So you want a subcommittee, you just want 3 out of the 5. How many ways subcommittees could be formed? So here you have N as 5 and you are choosing 3. So this is it. 5 times 4 times 3 times 2 times 1. This is your 5 factorial expansion. 3 factorial is 3 times 2 times 1. This is the expanding your factorial. And 5 minus 3 is 2 factorial. Expanding this is fairly easy. So 2 times 1. This is from the 3 factorial and this is from the 2 factorial. I love to make my life easy, so I'm just gonna cancel this out. 3 with 3. I'm left with 5 times 4 divided by 2. So 5 times 4 is 20. 20 divided by 2 is 10. So I have 10 possible ways of selecting 3 subcommittee out of the 5. Okay. Okay. I want a 5-minute break because I'm tired. So now it is 10:25. Let's come back to at 10:30. If you have any questions, please ask me within this time. We have half an hour to go. No questions? Okay. I'm going to assume everyone understands. So you guys are ready for quiz? Just kidding, just kidding. Where should we have the quiz? So week. Let me share the academic calendar. Okay, so I think your first test is going to be on either week 5 or week 6. So let's plan for a quiz in week 4 or 3. Let's have it on week 3 on Wednesday. So now it's week 2. So one more week. Next week on Wednesday. Let me write that down somewhere. See. What was that? ENG. I think you guys are quite quiet for a 60 student class. Okay, ENG. So let's have our quiz on next Wednesday. Will topics covered all topics that we have learned will be covered. Okay. And then our second quiz will be between test 1 and the final exam. Wait, do we have a test 2? Test 2. I'll open this. We don't have test 2.
Doktor, quiz face to face ke?
Sorry, again?
Quiz face to face ke?
No, it's online.
Okay. Thank you, Doktor.
Yeah, okay, welcome. But we will have 2 quizzes. So the first quiz is just going to be 5%. It's just like a preparation for your first test lah, actually, so that you don't wait until the last minute to study. So we have test 2. Test 2, I think, is in week 10. Week 10, and then final exam is after week 14. Project is 10%. Oh, I haven't discussed project yet with you guys. Okay, that's on the list as well. Okay, so I told you guys the quiz will be online, but it is going to be randomized so that you guys can't cheat. I won't tell you how it's going to be randomized, but you won't get the same questions. Okay? Stop sharing. So please prepare well. 5% isn't much, but it can make or break your grade if you want an A. Sometimes it is important. If you want to get a B from a C, that 5% is definitely important. Let me share my screen again. Week 3, so I have another week to prepare. Okay. Oh, malasnya. Okay, never mind. Stop sharing. You guys are lazy for quiz. I'm also lazy to prepare questions. Okay, so it's also hurting me. I don't want this. Stop sharing. Okay. So let's continue. That was a long break, 7 minutes. Never mind. Okay, again, refer to the student council scenario. Remember that we were talking about, we have 7 representatives from each department, and from the 7, we chose 3 subcommittee. No, wait, we chose 3 subset, and this was for the ordered subset. It was either chair or vice chair or secretary, right? And then we also talked about the student council scenario, whereby we have 5 representatives and we want to select 3 subcommittee. We have 2 examples relating to the student council scenario. Suppose that 3 of the 7 representatives, right? Suppose that we have 3 of the 7 representatives to be selected to attend a nationwide leadership conference. So now when I select these three, I don't really care assigning them as like presenter or assigning them as writer, assigning them as a poster presenter. So I don't really care about that. I just want to select three and I want to have them attend the conference. So here, the order is not important. The order of selection is not important. All that matters is which three that gets selected. So here we are looking for 7, choose 3. Here we are using combination, not permutation, because the order is not important. So C, 7, choose 3. What is the equation to write? It is 7 factorial, and then we have R factorial, 7 minus 3 factorial. Okay, so 7 factorial, we have 3 over here. Okay, so let's do this. I'm going to be brave and write this down. 4, 3, 2, 1, and then denominator 3, 2, 1. I'm just putting this here. Don't do this on your exam paper. 7. Wait. This is not 7. 7 minus 3 is 4. So 4 times 3 times 2 times 1. So again, let's make our lives easy. Let's cancel this out. 3, 3, 4, 4. Then we are left with 3 times 2 is a 6. Cancel this out. I'm left with 7. So there's only 7 ways to select 3 out of the 7. That's not a lot. Okay, so that is how you do it. Make sure to not make a mistake here. I don't know if our calculators can use factorial or not. Can we? Can we use factorial in our calculator? Oh, I think we can. So it's the same, it's under the mode button. So 2, let's see, 5 factorial. Oh yeah, we can. Okay, that's cool. So hopefully no one makes a mistake in calculating. So the thing to take note here is identify whether it's an ordered subset or unordered subset. Second, which equation should you use, permutation or combination? So those are the things that matters, and the rest is just your calculator. Okay, next example, a number of ways in which 3 cards can be chosen or selected from a total of 8 different cards. So here we're not assigning anything to the cards, so the order of choice is not important. So sometimes they can write permutation or combination like this, 8, 3, like this. But we're going to use like this, We're going to use like this, 8, choose 3. So here, they're just expanding it. I don't think we should do it. It's quite redundant. Okay, exercise number 7. Okay, this one is a little bit confusing. So I want everyone to pay attention. A box contains 6 M&Ms. Again with the M&Ms, 4 red and 2 green. Okay, so a child selects 2 M&Ms at random. So the child selects 2 M&Ms at random. So here we can already say that our subset is 2, right? Out of the 6 distinct, not really distinct because they have the, okay, never mind. So we have 4 red and 2 green. A child selects 2 M&Ms at random. What is the probability that exactly 1 is red? So instead of listing out all the possible combinations, we want to use either permutation or combination. So why did they choose combination instead of permutation? Why? I know it says here the order of choice is not important, but why is it not important here? How can you identify that this question is not a permutation question? What is the giveaway in the question? What is the tip? Anyone wants to try? It's okay if you're wrong. Okay, I'm going to repeat my question here. So here, a box of M&Ms, a box of 6 M&Ms, 4 green and 2 green, 4 red and 2 green. A child selects 2 M&Ms at random. Here, the solution says to use combination instead of permutation. Why?
One box have 4 red and 2 green.
So why is the order not important?
Because the child select M&M at random. So
M&M at random, okay. Okay, any other answers apart from that? So do we have stages here? Do we have stages whereby the child has to select the first one and then the second one? Do we have stages?
no.
No. So if we don't have stages, it means that we don't have order. So here the child is selecting 2 at once. So there's no order. He's just selecting 2 subset. Sorry, the subset is size 2. Versus if I say I want to select 2 M&Ms and I want to make sure the first one is a certain color and the second one is a certain color, the subset is still 2. But now I have stages. I take 1 at a time. So that is your order. But now the child is selecting 2 at a time. There's no order to it. It's just done in a single instance, right? So that is your way of identifying whether it is an ordered or not unordered subset. So that is very important. The question doesn't spell it out to you. You have to know how to identify whether it's a combination or permutation. So that's the hard part. Okay, so here we are choosing combination 6 choose 2. 6 choose 2. So there are 15 possible ways to choose 2 M&Ms. But the question is asking us, what is the probability that exactly 1 is red? So here we have, here they are using combination 2 choose 1 because this is the number of ways to choose 1 green M&M, sorry. Because when you want something that, when you are selecting 2 M&Ms, you want exactly 1 M&M that is red. It means that the other one should be green, right? Or both reds. Tetap. So here they are calculating the ways to choose a green M&M. Here they are calculating the number of possible ways to choose green M&Ms. So I only have 2 green M&Ms. If I only get to select 1 because the other one should be red, so I need to have 2 choose 1. The subset for this green is 1 out of 2. Okay, bear with me. Let's just go on with this first. And then if I have 4 red, I want to choose exactly 1 red when I choose the 2 M&Ms. So I have 4 reds, choose 1. So combination of 4, choose 1. So this is the number of possible ways to choose 1 red M&M. So now, assuming that I pair the reds and greens together, the red and green, so the number of possible ways to get 1 red and 1 green is 4 times with 2. So here they use the product rule. And 1 and 2. There are 4 possible ways to choose red M&Ms. There are 2 possible ways to select 1 green M&M. So the probability, this is our frequency to select 1 red, 1 green. This is our frequency and this is our N. Okay, so now our P, the probability of selecting exactly 1 red only, which means that the other one should be green, is frequency over N. Frequency is 8 over here, and our N is 15. Sorry, just now I said at least, it's exactly 1. So 1 red, 1 green. You can't have like 2 reds. Okay, so should I repeat myself here? Does anyone want me to repeat?
Yes.
Yes, okay. So let me erase this. Okay, let's go over the question again. A box contains six M&Ms, 4 reds and 2 greens. Okay, 4 reds and 2 greens. For entertainment purposes, I'm just going to draw this. Okay, we have 2 greens. A child selects 2 M&Ms at random. We already know it selects 2. It doesn't care about the order. There's no first try, second try. There's no order here. There's no stages. It is selecting 2 at once. So you know that this is a combination problem. You have 6 selecting 2. The subset size is 2. Okay, so what is the probability that exactly 1 is red? Exactly 1, not at least 1. So if you say exactly 1, which means that you can only have 1 red and the other one being green. If the question says what is the probability of at least 1 red, then you have to account for M&Ms being both red. But this is not the case. The question says exactly 1 red. Satu je, just 1 red. So if you have 1 red already, the other one has to be green. So now we want to know what is the possible way, what is the number of possible ways to select 1 red M&M and 1 green M&M. So to do this, we get a subset of 1 from out of the 2 greens and a subset of 1 out of the 4 reds. So here, I want to know what is the number of possible ways to select green from here. So 2 choose 1. So I get the answer is 2. And for this guy, I get, so this one, and the number of n is 2. 2 possible ways to select green. So now we're talking about red. What are the number of possible ways to select red from this bunch? So the number of possible ways is 4 choose 1. So the answer is 4. You have 4 possible ways. Now remember, the product rule says it allows us to calculate the total number of events. The product rule tells us the total number of events. So here, there are 4 possible ways to select red, and there are 2 possible ways to select green. This is the first stage and this is the second stage. We can call it like that, even though this is not an ordered subset. We're talking about product rule here, okay? So this is the first and this is the second. Remember, the product rule tells us N1 times N2 is the total number of events. So here I'm multiplying 4 with 2. So the number of events is 8. Okay, so what are the chances of selecting 1 red and 1 green? The chances of selecting 1 red and 1 green is just 8. The frequency of that happening is 8. What is the total number of selecting M&Ms? Selecting 2 M&Ms from the 6. This is where you get the combination of 6 choose 2. You don't really care what you get. You don't really care if it's 1 M&M, 1 red M&M or 1 green. You just want to know how many ways can you select 2 M&Ms out of the 6. So this is where you get the 15. And the second question asks you, what is the probability of selecting 1 red and 1 green? This is me breaking down this question. What is the probability of selecting 1 red and 1 green? How many times does that happen? It happens 8 times. So 8 out of 15. Now, if this is not clear, we can try to list it out. So let's do that. Because there is only 15, but I'm lazy. So it's okay, we'll do it for everyone to understand. I need space. Do I really need space? So let's use this one. So this one, it lists out the number of events, right? For the first M&M, there are 3 ways to select the first M&M, and then for the second M&M, there are 1, 2, 3, 1, 2, 3, you know, all those stuff. So here, if we try to apply this with our example just now, so I want to know how many reds that I can select. How do I do this? How do I break this down? I need to draw this somewhere else. Does anyone know how to list it out?
What did you see that?
What was it?
I mean, what's your question?
Okay, so just now we used the product rule and also the combination to determine the probability of selecting one red, right? So how do we list out like this table instead of using the formula? Anyone wants to try?
Doctor, was this the 4 red, 2 green one?
Yes,
The-
4 red and 2 greens, yes. We want to apply this
4 red
table.
and 2 green.
Yeah, we want to apply this table, but for that question.
If I'm not mistaken, will it be red, green, and then green, red? Red, green, and then green, red. Let me see. Or green, red, greens.
So how do we list it out? Okay, I'm gonna give you a hint. So the red is not R, 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 it's R1, R2, R3, R4. Is that a good enough hint?
Okay. I think I got it. R1, R2, R3, R4, and then it will be something like R1, R2, R1, R3, R1, R4, and then R1, G1, R1, G2.
Yes, so the
And then
total
we
number
continue
of...
with the different order.
Correct. Okay, so let's write that down. Or should I assign that as exercise? So we have 10 more minutes. I have one more example. Give me a minute. Okay, so it is helpful to imagine the R not being RRR, but instead R1, R2, R3, R4. 1, R2, R3, R4, and the greens as G1, G2. So that is your hint. So what are the number of pairs that you can form with this? Should be 15. Try to list it out and see what you get. Okay, so I'm going to move to the last example. This example is quite important. In a nutshell, how to differentiate between permutation and combination. So we have a movie, an old movie called Madu Tiga. It's a P. Ramlee movie. I don't know if you guys know this. I also don't know, but I was forced to learn this. So for example, Abu is given a chance to choose 3 women as his wives. Not a very nice example. So Abu is given a chance to choose 3 women as his wives amongst 5 pretty women, Aminah, Salma, Eton, Esa, and Joya. This is from the movie. So there are 5 candidates. He only gets to choose 3 wives out of the 5 candidates. So do you use combination or permutation in this case? Is it combination or permutation?
Commutation.
Combination.
Combination, right? Because we don't care who becomes the first wife, who becomes the second wife, or who becomes the third wife. But if Salma said, I need to become the first wife, or Eton said, I need to become the second wife, now that is when the order is important. So now this main character has to decide who becomes the first wife, who becomes the second wife, and who becomes the third wife. Now we have that order. So when you have to choose who from the three you have to choose who becomes the first, second, and third. Then you will be using permutation. Okay, I don't know if this example is helpful, but if you need to remember permutation versus combination, you can use this example, or I hope I can find a better example than this. Okay, so this is the first case. What is the probability that Etun, Esa, and Joya are chosen as the first, second, and third wife? Here, order is important. Case 2, what is the probability that Etun, Esa, and Joya are chosen as the wives? Here, you use combination. You use combination to get the frequency. So combination of 5 is your frequency. Choose 3. Here, the order is important. Permutation 5, choose 3. This is your frequency. How do you get the n? Remember, probability of something is f over n. How do you calculate n? For this case. Jam, jam, jam. So that's for another time. Okay, so that's it for today. If you have any questions, you can ask me. Otherwise, we are done with class. And this recording will be available on YouTube as usual. Okay, take care, everyone. Have a great rest of the day. If you have any questions, you can ask me.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Bye.
Thank you, Doctor.
Thank you, Doktor.
Uh,
Jumpa petang, Doktor.
Jumpa nanti.